name is Kai Stinson, and today I'm going to be doing a screencast to show how I use Desmos when solving or demonstrating geometric or properties, construction properties, and processes for constructing geometric figures. So let's get started. So I'm actually going to be building a quadrilateral. So I'm going to take my line segment, and I'm going to build undo that. I'm going to build a quadrilateral of any kind. So it doesn't necessarily have to be a square, it just has to be a four-sided polygon. There we go. Ta-da! And then I'm going to create some midpoints. So if I go down here, we've got this midpoint tool. I'm going to grab that and click my sides, respectively. Now I got my midpoints. Then I'm going to go back and I'm going to label up my sides. We're going to call that label E, label F, label G, and finally the last label, label H. Here we go. And we're going to name our other labels A, B, C, and D. And next, I'm going to create another quadrilateral inside of this quadrilateral, but it's going to be a midpoint quadrilateral. Much like the name implies, I'm going to connect these points all together. Voila! There is your midpoint quadrilateral. Now let's take a look. I'm gonna go through and explore the shape, and I'm gonna come up with three conjectures about it. The first thing I'm gonna state the fact is that, first of all, it's a quadrilateral, and as long as I have four sides of any length, shape, or thereof, they don't necessarily have to be parallel. So I can really stretch this guy out, and I can make it a kooky shape. So like that. But as long as I have four sides, I'm good. And during that, I'm also going to state the fact that no matter what orientation I make my ABC quadrilateral, my E, F, G, and H will always be midpoints, will always retain the shape of another quadrilateral, and will be always in the interior of my quadrilateral. The other thing I will note is another conjecture, the fact that we also have four triangles in here. Triangles AFE, triangles EDH, GCH, and FBG. I'm going to go and I'm going to make another conjecture to say the fact that these triangles are similar triangles. Not in the sense that they're congruent, but that they are similar, meaning that they have a similar ratio in their sides or their angles. And you could calculate that, but I'm just worried about making these conjectures. So to reiterate, I'm making three conjectures. First of all, I'm saying the fact that this geometric figure is a quadrilateral because it has four sides. The interior of the midpoint quadrilateral is midpoint because all the points are always at the midpoint, no matter what orientation my base quadrilateral A, B, C, and D is. And finally, I'm stating the fact that the three triangles that can be formed from the midpoint quadrilateral and the overall quadrilateral they are all similar. Some of the different strategies that I'm using to determine this, however, is that I'm dragging these points in orientation, but I'm making sure not to do the following, which is what I'm going to demonstrate what you would not want to do, and that's this. All my conjectures have now just been completely shot. They don't work anymore. For starters, I will say, however, that two of them, now that I consider this, two of them actually might be, but it's a stretch. That would be the midpoint conjecture and the similar triangles conjecture. Even then, I would not be too certain because my first conjecture has gone out the window because this no longer is a four-sided polygon. It does have four lines, yes, but it's not. The lines aren't. The lines are crossing each other. They're not. They are not sharing the same. Well, they're not parallel. So they're not parallel, but they're not. They're not acting. Oh, look at that! It's 3D. little easel looking thing. But they're not. They aren't. They're crossing basically, and those points also aren't defined either. So wherever they cross, for example, like in this case, the points that are defined where they would be crossing. Let me go back and make the really just the ugly shape that I had earlier. So I'm just going to move these back. If I go like this again, the points where they're crossing, which would be here, for example, lines AD and BC, that point isn't defined. And because of that, it doesn't hold true because I had to define that point in order to even consider it to be a four-sided shape again. Because right now, these are two, and I'll highlight the other one. I hold down Shift to do that. You can see that point's not defined. Technically speaking, these are two separate lines. If that was defined, then this would no longer be a quadrilateral. So in order for this to be a quadrilateral, I still only need four lines, but the orientation of it doesn't make it look like that. So you have to be careful because your orientations do matter. Let's see here. And then I have one other thing I want to talk about here. So let's take a look. Let's take a look at some of my conjectures. I'm going to take a look at my conjecture about the triangles because there's something interesting about those. So I'm going to go over here and I'm going to make a conjecture that the length of the sides of each of these triangles, that the length from here to here is the same, and the length from here to here is the same, and the length from here to here is the same. Therefore, that these triangles should have ratios that are all the same. So let's take a look at that. I'm going to make some quick segments from B to H, and I'm going to get a measure of that. There we go. And I'm going to take another one. I'm going to go from B to E, from there to there. So I'm going to go around and I'm going to get all my two sides of every single one of these triangles that I have in here that we're seeing. Okay. And we're going to go through, we're going to select this one. We're going to select this one. We're going to select that one. Oops. We're going to select that one. And that one. And that one. And finally, that one. All right, so my proposal is that the lengths of my triangles, no matter what I end up doing to these, okay? So let's say, for example, that in a perfect world that, and we'll get these as close as I can. Well, let's just say that we're going to round. So we have basically legs that are, we have legs 4. Let's round these up to 5. So this is basically 5 and 3. I'm rounding these because I want to get a 3, 4, 5 triangle. And I'm going to propose that my value from H to E is somewhere rounded up or down to the value of 5. So I'm going to take this, I'm going to come over here, I'm going to then select this, and we're going to add the length. All right, it's a little higher, but like I said, we're not being too finite with our exact measurement, our exactness as far as the drawn sketch. I wanted this to be a free-form figure, and there again, see, right beneath 6 again, and right beneath 6. So my conjecture on the fact that these 4 triangles made up from the 2 quadrilaterals, the midpoint and the overall, are all similar triangles and possibly could be congruent. But similar is a bit better because there's more given the fact that it doesn't actually have to be identically equal in distance, but they can be congruent. So in other words, it goes in order of importance of the conjecture. I would list them out as similar, congruent, equal. That pretty much takes care of what I want to talk about today. I hope this was a good example of how I use a geometric tool like Desmos to display and answer questions about quadrilaterals and the different requirements of that. I hope you guys have a wonderful Easter weekend, and thank you so much for watching this video. Bye-bye.